Good afternoon, everyone. Yeah, warm greeting to one and all present here. Myself, Selvamina, Assistant Professor, Department of Computer Science and Engineering of Dr. MGR Educational and Research Institute, and one of the coordinator of this FDP program. With a great pleasure, I welcome all the participants to this 5 days online faculty development program on next generative AI, exploring the power generative model and the transformer, organized jointly by Department of Computer Science and Engineering and Department of Cybersecurity of Dr. MGR Educational and Research Institute. To formally start this event, I now request Dr. N. Ethiraskar, Dean ENT, to deliver the valedictory address. Please, sir.
Hello. Hello.
Good
Audible,
evening.
sir.
Okay. Good afternoon to all. See, I'm really happy to note that the Department of Computer Science and Engineering has organized a 5-day FDP on next generation AI, exploring the power of generative models and transformers. And in the past 5 days, they have arranged a lot of experts from academic as well as from industry. I hope that the faculty members would have gained some knowledge on AI, especially future AI. And then, as we know, the AI is, included in almost all domains of life. And the way in which it is actually developing and advancing is really, you cannot imagine. And now it has become a call of the day for each and everyone existing in the earth. And now only my request to all the faculty members is to actually make the awareness of AI to all, not only to the students, but even to the society. At the same time, they have to adhere to the ethical values of the society, and they have to use the AI in right sense. That is very, very important, because you know that whenever anything is positive is there, always the negative will also be there. We have to take care of that negative side and we have to sort it out. So this is one of the danger actually in all fields where we are applying AI or ML, even though it is doing a very good, excellent work in respective domains. I again, we are actually facing a lot of problems in day-to-day life. They are seeing that using the AI. Even cyber crimes are increasing because of AI. And one of the very important thing for our academicians is to make the people to understand the importance of AI. At the same time, we have to see to that it is used in the proper way. So with that note, I really congratulate the team of Computer Science and Engineering Department, especially Dr. Geeta, HOD and Dean of Computer Science and Engineering and his team for organizing this wonderful topic to advance your knowledge. You can to enhance your knowledge. Thanks a lot. Thank you.
Thank you, sir, your valuable speech. So today we are privileged to have with us Ms. A. Joshini Lobo, consultant. Ma'am, now I invite Dr. G. Victor Sudhakar, additional HOD, Department of Computer Science and Engineering, to give the brief introduction about today's speaker.
Good afternoon, all. It's my pleasure to introduce our esteemed speaker of today's session, Mrs. A. Joshini Lobo, consultant at TCS Chennai. With over 23 years of experience in the technology landscape, ma'am has built a career grounded in deep technical expertise, multi-domain exposure, and hands-on leadership across AI, software engineering, optimization, and large-scale distributed systems. Her journey spans roles such as machine learning engineer, data scientist, and architect for large Python-based intelligent applications, giving a uniquely integrated perspective across research, engineering, and enterprise production system. She has begun her career in mainframes where she has designed and built highly reliable backend platforms supporting retirement systems and employee healthcare benefits for major US retailers. This foundation in high integrity, mission critical systems continues to shape her engineering approach today. Over the years, ma'am has worked extensively across healthcare, retail, and banking, delivering platforms that combine data engineering, advanced modeling, and design intelligence embedded into operational software. Beyond machine learning, she has deep expertise in optimization, having designed and refined systems using linear and non-linear programming revenue management problems. A significant part of her work has begun in deep learning innovation. She holds granted patents for novel neural network architectures developed to solve complex time series forecasting challenges in retail, especially around demand prediction and long horizon predictive stability. These models have been deployed at scale and have directly improved forecasting accuracy and inventory decisions for enterprise clients. She has also been into accelerating computing, working in collaboration with NVIDIA to design, optimize, and deploy neural network architectures on distributed GPU system. This includes performance engineering, parallelizing deep learning workloads, and enabling high throughput training and inference pipelines. Currently, MAM works span agentic AI systems, intelligent application design, and the integration of analytics, optimization, and automation into high impact production solution. She operates at the intersection of mathematics, AI, and enterprise engineering, driven by a commitment and applied innovation and continual learning. Ma'am, we are honored to have you with us today, and you are truly the right person to lead today's session, and we look forward to gain valuable insight from your expertise. Thank you, ma'am. We welcome you for the session.
Thank you. Good afternoon, all. Hope I am audible.
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Yeah, I'm sharing my screen, ma'am. Can you please confirm if it is visible? I'm not able to find the share option, which was, yeah, it is there. 1 second.
Ma'am, you just go to settings.
Yes, ma'am.
You go to settings. The
Yes.
statistics on share is there. Paramasivam, am I correct? Statistics, you have share. That is different. That is different.
The bottom share button is there.
Share screen is there, ma'am. In the bottom.
Screen is there, ma'am, but I think I have to also allow it from my system too.
You click the share button, it will lock the entire screen or any.
I think I have to change something on my system, ma'am, and if I have to allow Zoom to share my screen.
Okay.
System settings, security and privacy.
So you could not able to do it. Yes, ma'am? Either you just give your presentation to us.
Yes, ma'am. 1 second. Is my screen visible now, ma'am?
Yes, visible.
Yeah.
Yes, ma'am. Visible, ma'am.
Yeah, thank you, sir. So the topic for today's session is about how do we effectively or efficiently design and build agentic systems. Okay. Right now the buzzword is all agentic AI. So we started with machine learning, then it was deep learning, then we moved on to generative AI. That was the next thing that was happening in the AI world, and generative AI slowly evolved into what we call as agentic AI today. So what is an agent? So an agent, basically, it has the ability to do things for us. So we can automate a lot of our stuff, a lot of things that are done in enterprises and organizations. A lot of tasks can be automated using an agent. So we are going to see what is an agent, where does it fit into the generative AI world. So an agent, basically, it uses an LLM and it also has the ability to act. It can do actions. We would have all used the ChatGPT, the UI, with the UI interface. We would have put in our queries, the ChatGPT gives us answers. So that is basically, it is a chatbot kind of a thing which will not do any kind of actions for us. So the ones that we typically use, the ChatGPT that we typically use doesn't do any actions for us. When we upgrade the ChatGPT plans, then we are able to book travel. We are able to do our personal shopping using ChatGPT. So that upgraded ChatGPT is an agent, whereas the default, the free versions or the basic paid version that we use, typically it is only an LLM. It is not an agent. Why it is not an agent? It is because it's not able to do things for us. It can only generate text for us. Whereas an agent will be able to take actions. So it will use LLMs, it will use tools, and it will also interact with the external world and get things done for us. So that is what is called as an agent. So this whole session is about how efficiently we have to design those agents using LLMs, using tools, how it has to interact with the humans outside, and what kind of actions it can perform, how we can control the agents. So the entire session would span around this area. So the core concepts of an agent, if you see, it will usually operate in a looping system. So wherein it will observe the question the user had asked or the task that the user had asked the agent to perform. It will analyze the task, it will reason out, it will plan the actions that have to be taken to complete the task, and then it will act upon the plan that it had come out with in order to accomplish the task. And then finally, in this whole process, we have this thing called as state. So the state is nothing but it is a sequence of actions that have to be performed. The agent has to perform in order to accomplish the task that the human had asked the agent to perform. So in that whole course of action it has to perform, the workflow, there is data that has to be transmitted from one action to the next action to the next action in order to complete that task. So that is what we call as state. So the whole idea of an agent is usually it typically operates in a looping framework. It has memory. So it can remember what we had asked the agent in the previous action or the query that we had given to the agent. It can retain things, and it has some goals to complete. Okay. And the third thing is it basically the agent enables us to automate tasks. So these are the key differences from the LLM. LLM, we do not operate in a loop. Maybe in the ChatGPT version that we use, we are given an illusion that it is operating in a loop. It can remember the prior conversation, but it does not do any task. It doesn't have any goals to complete. It just, the only goal it has is whatever the user had asked in that particular session of the chat, it can only respond to that user's query, putting in some text as a response. So this is how the agent has to be developed. It usually operates in a loop so that its intelligence emerges. Its intelligence keeps evolving over a period of time. Whereas LLM, it just gives a response and it is done with that. Whereas this agent, it has to operate in a loop. Now let's see the key differences between agent versus LLM. So LLMs, they are only meant for generating responses, whereas agents take actions. LLMs are stateless, meaning there is no data flow between the prior action and the current action. Agents, whereas they maintain the memory. So that is what maintaining the memory is what we call as context. And the state keeps evolving from one stage to another. The LLMs, they respond only once, whereas the agents, they continuously interact with the humans. They understand what they have to do if there are any queries, and it is a kind of continuously interactive phase until it meets the goal. LLMs use text only, whereas agents will use tools. It will make API calls. It will invoke other external systems, connect with database servers. So there are n number of things that the agents do because it has access to tools which the LLMs do not have. LLMs follow prompts. So LLMs are purely driven by prompts, whereas agents are driven by goals, their plans, and the rules. So from these days or off late, the latest bubble in the AI world is agentic AI. So we are shifting towards agentic systems. So from passive chatbots, we are moving to active agents. There is going to be a lot of tool integration, multi-step reasoning. Instead of just interacting with the LLM once, we are going to interact with the LLMs in a looping manner, so that the reasoning part is done in several stages of phases, and it improvises the plan, it improvises the work that is done by the agent. And we have end-to-end workflows. So basically the agent can be treated, or the agentic AI can be treated as a workflow mechanism wherein the goals are broken down. Each goal is being split into several actions. The actions are carried out. If required, corrections are done, and then the entire task is completed. So agentic AI is nothing but AI in a workflow. Okay. So now next is, what are the non-technical skills for building the agents? So we know that the popular frameworks for building agents are LangGraph, we have Crew AI, we have AutoGen. So there are so many frameworks available to build the agentic AI stuff. But what are the non-technical skills that are required? And this is where any tutorials or any kind of ChatGPT questions that you ask would not cover as to what other skills are required to build efficient agents. Okay. The first one is problem decomposition. So let's take an example that, okay, we need to build an agent. Being in the education field, let's say you want to submit a research paper, or you're doing your PhD thesis. You need to figure out what is the problem statement in your area that you would like to address in your thesis, in your research, basically. So let's say we plan to use an agent to complete your research, to do the research on behalf of you, to do the research, to find out first let's find out the research topic. Then you need to analyze the solutions for that research topic, and then you have to write up the entire solution, have a prototype for that solution, and finally final stages, let's say it's the submission of that research paper. So these are all the tasks that you as a researcher is supposed to perform. Now, if there is no agent, if there is no AI, this is the list of tasks that you would typically perform. So as a human, you would first analyze, look for a suitable topic on which you can perform your research. So you get the research topic. So basically what we are doing here is we are taking the entire task of submitting a research paper, and we have to decompose that problem into several steps. So whatever you do in real life, whatever you do as a human, you are replacing it with an agent. And when you replace it with an agent, you need to ensure whatever effort you make or whatever effort you put in towards your research paper, the same effort the agent has to put. All right. So whatever the task that you do, you have to convert it into activities or the steps for the agent. If you, in order to complete your research paper, let's say you are looking into the archive repository to find out for suitable problems that exist for which there is no solution, or for which there is no complete solution. So you need to search the archive repository for a suitable problem statement. So yes, have a tool built for that. Have a tool that will access the archive repository using some certain credentials that you have, and this tool will search the archive repository. Next, you got some suitable problem statement. Next, what you would do? For that particular problem statement. So you will do a web search here. That would be your next step. Third step would be you have to come out with solutions. Come out with solutions that are very unique. So you have to kind of form a hint as to what kind of solution you intend to propose for that problem. So provide your hints to the agent. and the agent will further do analysis on that hints that you have provided. It will go and further, you will try to further search the web to see if there is a similar solution or if your solution is unique. So that again is a task that you perform. Next, when you find that the solution is suitable, you need to write up the solution in the format that the research paper essentially requires. So again, you have a certain research template or research paper template that you have to follow when you write your thesis. So these are the steps that you typically do. And typically what you're going to do is you're going to build an agent, and the agent will be having access to web search, will be having access to do an archive search, will search the web, will analyze your hints, it will come out, write a research paper on behalf of you, and then you pass it on to your supervisors to review your research paper. So likewise, you can have a reviewer agent to review your research paper, and then it will provide some improvisations on that, and then you work on that improvisations. So rather you can make the agent rework on that improvisations given by the reviewer agent. So now you get the context, right? So the agent is nothing but it is replacing the human. So exactly whatever you do, you need to follow the same principles or the same hierarchy to decompose the task that you have on hand and in order to build your agent. So that is the very first essential skill that you need. You need to know how to decompose the problem statement that you are planning to address using an agent. So this is the very first skill, problem decomposition. And next, domain understanding. So let's say you'd like to do a research in embedded systems within the computer science domain. So this, I'm not sure if embedded systems come under computer science domain. Let's take the example of embedded systems. So we need to have an LLM that is knowledgeable on embedded systems. So when we use an LLM in order to analyze the solution that we are giving it to the LLM, we are just giving hints and we want the LLM to develop that solution. So we need to specify to the LLM that, okay, you are an expert in embedded systems and you are an expert in so and so problem. So this is how I intend to solve this problem. So can you please analyze if there are any loopholes, if there are any further improvements in my solutions. So this domain understanding that you need should also be transferred to the agent. So you need to understand that, okay, the domain knowledge also has to be available to the agent. Next is prompt design. So in order to make the LLM or the agent work for you, you need to provide instructions. And the instructions are supposed to be very clear. You need to tell the LLM what it can do, what it cannot do. For example, the solutions that is presented for the problem that has been identified has to be unique. So provide that as an instruction. Constraints. Tell the agent not to use any prior solutions that are already available in this field. And then you need to say what is the workflow that the agent has to typically follow. So you have to say that, okay, analyze the web for me, search the web for me, get the search results, link all the search results together, analyze them, see if there are any gaps in the solution. So all those things have to be clearly, the instructions have to be clearly passed on to the agents. So it's more of a clear, concise communication that is an essential skill here to build an agent. Next is systems thinking. So in this whole process, you had decomposed what is the task on hand, you have decomposed into smaller steps. Now you have to visualize in each step, what is my output? And in the next step, how am I going to process that output? What is the data that has to flow from the first step to the third step? What decisions have to be taken in this step? If there are any issues, so let's say the archive doesn't return any search results for the research topic that I'm looking for. So what is my next step if archive doesn't give me any results? Should I look into the web? Or should I have a new research repository that I should be looking into? So you need to visualize the end-to-end process or upfront you have to visualize what is that you will do in order to write a research paper. Then the next skill that is required is UX awareness. So basically, at what point the agent has to interrupt its flow, take a break from its workflow, ask questions, write questions to you for it to further continue its task. So you have to design your agent in such a way that the agent knows when to break off its loop, when to interact with you, when to get what kind of queries it has to pose to you, and how it should process the response that you are giving back to the agent. So all those things have to be imbibed into the system. So when you design your agent, you have to ensure you provide provision for this human interaction. Next is risk awareness. So you should know possibly what can go wrong with an agentic AI system. Where are the possible failures that can happen? How can you safely ensure that the agent doesn't go rogue, doesn't do anything wrong for you? It works as expected for you. So you should be aware that building agents, getting things done for you has its own pitfalls. And when you design your agents or build your agents, you need to ensure that you address most of the pitfalls and ensure that the agent doesn't work against you. So that is again another essential skill. So you need to know where the agents can go wrong, what can go wrong, and what precautions you need to tighten those loopholes. So this is levels of autonomy. So upfront, before you design your agent, you should know what level of autonomy are you going to provide to your agent. Does it want to execute the instruction as strict as possible? So you define you give a predefined order for the agent. First do this, second do this, third you do this. So that is the simple most agent wherein you have a deterministic sequence. You know that, okay, it is going to run, it is going to perform actions in this order. So that is the most basic level of autonomy that we give to the agent. The moderate autonomy would be like, okay, I have an archive tool and I have a web search tool. You can use either of them and then figure out suitable problem statements that I can address. So here you are giving some kind of autonomy to the agent to either look into archive or look into web search or do both. So you provide that kind of a freedom to your agent as to what tools it can use. Number 3 is the final end of the spectrum. You have this high autonomy wherein you leave completely to the agent to plan and execute things. So this is so as we go from one end of the spectrum to the other end of the spectrum, the autonomy keeps increasing, and you also need to understand that the risks associated with that autonomy level also keeps increasing. So these are some of the real world use cases where you can use agents to do stuffs for you. So this research and reporting is the use case we've been discussing throughout. Engineering assistance, here we have coding and technical support agents. So right now, if we see, we have this GitHub Copilot, which does the coding, entire coding for you. So you just need to tell what is your requirement. You can just tell the GitHub Copilot, okay, you build me an agent that will write research papers on behalf of me. So that this is at a very high level. You can also say that, okay, I want it to go look into archive. I want to search the web, first analyze the topic, and then write the research paper. So this is another level of input that you can give. So when you provide all these prompts to the GitHub Copilot, this GitHub Copilot will generate the entire code for you. So that's the reason why I do not wanted to take it as a very technical session, speaking on LangGraph or how you can use LangChain and all those stuffs. Rather, you need to understand the concepts, and those are just frameworks to get things done for you. So if you have the concepts, if you're well aware of the concepts, you can use them and you can build efficient agents. You can put in the right prompts to the GitHub Copilot and it will build it in the right way. So this GitHub Copilot is there, which only generates code for you. And recently you have this anti-gravity, which is again an agentic IDE platform that is released by Google. Okay, and you have some minimum access to all its premium models like Gemini Pro and all that. Claude, which does excellent coding for you. It not only does the coding, it will build you the requirements document, the implementation document, the design document. It does all the documentation work as well. So end to end, the SDLC process is taken care by this anti-gravity, which is released by Google. So so this is another use case wherein it's all done using agents. So this anti-gravity that I had told you, so it has multiple agents. So you have a dashboard kind of a thing wherein you can launch multiple agents with each agent doing its own work. So one agent you can say, okay, book my tickets to France, or another agent you can tell, okay, please build me a research agent. So and there is this dashboard which will give you a complete overview of what is the status of each agent, where it has how far it has completed your task, whether it was successful, whether there were any issues. If it has to ask for any user input, it interrupts its flow, it poses a question to the user. So all that is, this anti-gravity platform is something which everybody has to try out to. You will figure out how things are easier and simpler for you. So this is another industry examples. I've given a couple of examples here. So one is the legal draft. Of late, it was there in the news wherein people have, the legal experts have complained that new joinees into the legal field, all of them, they use AI and agents to come out with their draft, and they were not okay with that. So typical workflow, if you see, if we have to use an agent to review the draft. So let's say the legal advisor had drafted a legal contract. Now we need to verify if that contract is okay. So basically, a legal contract has to be reviewed by a human. So we build an agent for this process. So what the agent can do as part of its workflow, or this is the typical task decomposition that has been done. So it retrieves similar past contracts. So you can have a RAG system maintained which will have all the past contracts that your firm had created for a similar scenario. So you have a RAG, you can ask the agent to retrieve similar contracts from the RAG, and then you can check if there are any inconsistencies between the past contracts and the current drafted contract. You can flag the deviations, and then you can summarize what are those deviations in the current drafted contract, and then you can and then the agent can suggest revisions. So this is a typical workflow of a draft review agent. Likewise, for medical documentation also, there could be an agent. So the doctors, they have, as they visit a patient, or let's say an inpatient, so they come out with a note summary of what the patient, what is he being diagnosed for, what is his treatment plan, and how far is his progress. So all those things are being recorded in the clinical notes of the hospitals. So all these clinical notes can be put into a RAG, it can be retrieved, it can be processed, and then we can come out with the findings. So did this treatment plan work for this disease? Or which treatment plan was more effective? So it can come out with such findings, and then it can do this symptoms. It can map the symptoms to the treatment plans, and then it can suggest in future. It can use this to suggest what kind of diagnosis can be done for a particular disease. So this is another workflow wherein an agent can be used. So typically this work is done by a human. Now it can be done by an agent if you build an effective agent. Otherwise the outcome wouldn't be as effective as a human review. So our topic was design and building intelligent agent systems. So why should we worry too much about this design part of it? So frameworks, so I said LangGraph, LangChain, all those are frameworks available at various levels to build agents. So the frameworks might change, but all these principles that we are seeing now, all these concepts that we are seeing now, they do not change, they remain constant. And you can make use of the framework that is popular at the moment. For example, let's take LangGraph. So if you see LangGraph, 2 months ago, 3 months ago, there were so many revisions being released in LangGraph, and whatever things you developed 3 months ago using the LangGraph version that was available at that time is no longer supported by the current LangGraph version. So that is the kind of evolution we have on the agentic frameworks. So instead of focusing or putting our efforts too much on learning all these frameworks, instead if we put in a lot of focus in understanding these principles, these concepts around how the agentic AI systems have to be designed and built, that is more useful for us. And whatever framework is popular at that point in time, we can leverage that. We can use again the agentic IDEs, the anti-gravity I spoke about, or the GitHub Copilot, which is, again, it will cost you hardly 800 rupees per month. So you can make use of such tools, and then you can get things done for you. You can build agents for you. And whatever the Copilot or whatever the agentic IDE builds for you, you should have more knowledge to analyze, to review whether it has been built in the right way. So that skill is what is essential at this point in time, not learning LangChain or not learning LangGraph. All right. So what are the problems that can typically happen in agents, and why the agent's reliability might be a question? It can get into loops when it is doing tasks. It can hallucinate things. It can tell you things which do not exist. So you should be worried about agents being hallucinating. And then there could be unsafe actions. What it can, you wouldn't have provided a tool at all, but it could hallucinate that a tool exists. And then when it is trying to run that tool, the agent would fail. So you have to worry about the reliability and safety aspect. And then you have to see that, okay, whatever agentic AI systems that you're building is complete. And it is not just one LLM call, or it is not just one tool call that is there in your agent. Your agent has to be a complete system. Like how I said, writing your research paper, you need to think through what you do in order to finish that task. So whatever you do, that has to be translated into activities for agents. So it has to be a complete system. So all those understanding is essential in order to build a design, in order to design and build a super agent systems. So let's see about various design patterns for building your agents. All right. So the first one, so I was talking about, so let's go through this before we look at the agent patterns. So the building blocks of agents. So we already saw that LLMs are used in agents, tools are used in agents, and then there is orchestration, which happens linking LLMs and tools, and in what order these operations have to flow. So there are 3 key building blocks for an agent. So how these 3 building blocks are connected, or how the data flows between these 3 building blocks, is what the design pattern is all about. All right. So LLM, if you say, you can think LLM as the brain of the agent. It plans things for the agent. It reasons out, and then it finds what is the right order of steps to write your research paper. So it does the thinking part. It is the brain of your LLM. And the tools, if you see, it is like the hands of your agent, which gets things done for you. So this is where tools stand. And orchestrator is basically, okay, it will take the data, it will execute the LLM, it will invoke the LLM, get the response from the LLM, it will analyze the response from the LLM and decide what actions have to be taken, what tools have to be invoked. So the orchestrator does the controls the flow within the agent. It controls both the data part and the order of execution. So that is where the orchestrator fits in. So how these three components interact among themselves is what design patterns are about. So the first pattern we have here is the reason and act. So we call this as React pattern, not to be confused with React on JS that we have. So this there are two operations that are being done here, reason and act. So the LLM doesn't do any actions for you. It is the LLM only does the reasoning part. It thinks and then it figures out what action it has to be performed. So it just lists the actions that have to be done in order to complete your research paper. And then act, that is done by a tool. So the LLM just says, okay, you have to first search the archive. If you don't get any results or if you don't get sufficient results from archive, you have to do a Tavili web search. So Tavili is another mechanism, or it is an API which enables searching the web. So it just tells you what tools have to be called and when it has to be called. So it just tells you, it only reasons out that, the LLM only reasons that, and then the action is performed by the actual tool. So so in the case of React, you know you understand what LLM does and what the tools does. And then this cycle keeps iterating. So this is what is React pattern is about. Plan and execute. So plan is done by the LLM. It plans out what things have to be done in order to complete your task, in order to complete the goal that has been given to the agent. And the execute part does the execution phase of it. So the plan could list out 5 steps, and then all the 5 steps which are being listed out by the LLM in the planning phase will be executed subsequently in the next stage. So this is plan and execute pattern. The third pattern that we have here is planner, critic, and executor. So the planner is LLM1, which comes out with a detailed list of activities that have to be carried out to complete the task. So that is the job of the planner. So this is done by LLM1. The output of LLM1 will be given to a second LLM, which acts as a critic, which criticizes the output generated by the planner LLM. So now these two LLMs, we can either use the same LLM. So let's say we can use ChatGPT, ChatGPT 5.1, or we can use Claude, say version 3, or we can have planner as ChatGPT, critic as Claude model. So the planner and the critic can be either the same LLM or they can be entirely two different LLMs. So if you want an unbiased review from the critic, it's preferable to have a different LLM. So planner, critic, and then after the plan is being criticized, and if there are any issues with the plan, the criticizer can either fix it or it sends back to the planner. The planner can fix it, and once the critic okays that plan, it is being passed on to the executor, wherein all the actions listed in the plan can be carried out in the executor phase. Fourth pattern is the multi-agent collaboration. So in the case of your research work, you can have one agent to pick out a research topic for you. So that let's say topic picker is the first agent. So the topic picker will analyze archive, will analyze the web, reads all the research papers, finds what solutions don't exist for what problems. It does all the analysis, and then it presents a list of problem statements that are yet to be solved in your domain. So that is the job of the topic picker agent. So the output of topic picker agent will be now given to the next agent. Let's call it as analyst. So the analyst will go through all the technologies that are available in your domain, see what kind of solutions can be presented for the problems. So that will be the duty of the analyst agent. So this research paper problem that I spoke about, the use case that I spoke about, can be done at a very large scale by developing separate agents for each of the tasks. So that way the output would be more efficient, and it will be more useful. So this is where multi-agent fits in. So you can have a topic picker agent, you can have an analyst agent, you can have a research paper writer agent, then you can have a research paper reviewer agent, and then you can have an agent which will interact with a human, get feedback from the human, fix the feedbacks from the human, and then finalize the research paper. So then you can connect, make all these agents collaborate with one another. So that is multi-agent pattern. This would be a router or orchestrator pattern, which basically you tell how the agent has to go about this entire task. What has been executed at the current step, what is the output of the current step, based on the output of the current step, what should be the subsequent step. So all this is done by the router pattern. Here we have RAG agent pattern, wherein let's say we feed in, we have our own college repository of the research topics that our staff is working on. So you need to find out if any of your contemporaries are working on the same research problem. So you can build a RAG system. So whatever ongoing research is being done by your college staff, you can upload them into the RAG system. And then when a person who is about to start on a new research topic, he can go first using this agent. They can check if anybody is currently working on that topic within your college. So you can build a RAG system and use it as a tool inside your agent. So this RAG will retrieve information from your local repository, and it will give that context to the LLM, and then the LLM will analyze if the problem statement that you have picked up on, is it very similar to any other topic that is being worked upon already. And it will also generate a final summary as to, okay, you can go ahead with this topic that you had chosen, or there is a 50% probability that there is an overlap with so-and-so topic being worked on by so-and-so person. You can check with them and then proceed. So your LLM here is basically grounded. It doesn't use its own information. It doesn't hallucinate. It will only use the information that you have retrieved from the RAG system, and you feed it to the LLM. The LLM will only work on that information that you have fed into it. So this RAG agent pattern is nothing but having a RAG into your agentic workflow. Human in the loop, I think that this is obvious. The agent needs to take a break from its workflow, and then it has to interact with a human either for clarifying queries or for getting approvals then and there. So in the case of anti-gravity, if you see, before it gets the code generated for you for your task, it comes out with a solution document, and then it asks your approval. Whether if you approve, I will generate the corresponding code for this. If you feel that that solution is not sufficient, it is not making use of any good design pattern, you can specify that to the anti-gravity, and then it will fix its solution document, regenerate the solution document, come back again for your approval. So that is about human in the loop. This reflection pattern is more like the critic that we saw here. Here the critic does it on the plan. So the planner agent creates a plan, the critic criticizes on that plan. Whereas in a reflection pattern, so there could be a React agent which will, let's say, coming out with a research paper. It has come out with the first draft of the research paper, and here the reflection component of it. So in reflection pattern, basically there are two components. One is the generator component, and the other one is the reviewer component. So the generator component will be of this pattern, React pattern, wherein it will reason out and then act. And then it is coming out with the first draft of research paper. And the reviewer component will take that first draft, review it, and then come out with its feedback, send the feedback back to the generator component. So these design patterns are not something isolated. A single agent can have more than one pattern, So it all depends on how you design things. So in the example we just saw, there could be a React pattern, which is the pattern that the generator component uses, whereas the reviewer component, the generator and the reviewer component put together acts as a reflection pattern. Okay, so we saw about the building blocks. This is LLM. So now, what are the issues integrating LLMs within our agents? So the LLMs are prone to hallucinate. So how will you, so what is hallucination? So it gives us wrong information. It gives out wrong reasoning. It gives out facts which do not exist. It's fabricating the facts. So based on this, if the actions are taken, based on the hallucinated plan, if the actions are taken, then you would end up, the agent would end up doing the task incorrectly. So you have to be aware, you have to control hallucinations. So how would you control hallucinations? By using a RAG system. You can say, okay, this is your only context. Given this information, you have to reason and come out with a plan. Don't think beyond the information that I have given to you. Do not use your own information. Just use the information that I have in my system. So that is where RAG typically comes. So if you want your LLMs to work on your proprietary data, we build a RAG system. If we do not want our data to be exposed to the internet, but we still want the LLM to work on our company's data, on our college data. So we can build a RAG system. We can retrieve information from that RAG, and we can give that to the LLM and say, okay, provide your response based on this retrieved information that I've given you. And then there is another thing called as temperature, which we have to specify when we invoke the LLM. So the temperature of 0 means, okay, you're not going to be creative. We tell the LLM, don't give me any creative responses. Give me only information that is grounded on the facts. Don't give fabricated facts. So that is what the temperature factor controls. So whenever you invoke LLM, you need to be very clear on what is the temperature value that you specify. So another problem that we have here is unpredictability. So every time it creates its own output. So if you see the LLM, you ask the same question. If you ask the same question to ChatGPT now, and if you ask the same question the next very minute, it will give you two different answers. The underlying answers could be the same, the underlying facts could be the same, but they provide entirely different responses. So they are non-deterministic outputs. The outputs from the LLMs are completely non-deterministic. You cannot predict. It is not deterministic, meaning it varies. It varies from time to time. So again, that can be handled by stricter templates. So stricter templates means, okay, LLM, you don't give your own responses every time. If I have to write my research paper, I need to have an abstract section. I need to have a literature section. I need to have a solution section. So you just give me information under these three sections. So that is what we mean by strict template. So you provide an output template to the LLM. Tell the LLM, you please give me response only in this certain format. So that is possible. So that is one way of containing non-deterministic outputs. Wrong tool calls. So you wouldn't even have provided a certain tool to the agent. You don't even have a certain tool built into your agentic AI, but the LLM is capable of interpreting that, okay, there is this tool. So when you invoke the LLM, you need to be very clear, okay, only these tools are available to you. You can use only these tools to come out with your plan or with your list of actions that have to be performed. So the problem with LLMs in the system, in the agentic AI system, is it can return wrong tool calls. So one thing that you need to understand is LLM is not capable of doing any actions. It is only capable of planning. It is only capable of reasoning. It is only capable of generating text. It cannot do any actions apart from this. So in order to perform the actions, that is where the tools fit in. The LLM can tell what tools you can use. It can tell the agent what tools it can use to perform certain actions, but it never calls the tools. It only creates the parameters for that tools. So in order to do a web search, what are the terms that you need to use to search? So when we go to Google, we type out what we need to search. So that term that we need to type out in the search bar is what the LLM returns, and that's all. It doesn't do the web search for you. It only returns the text that has to be used for the web search. So you need to clearly have that kind of distinction as to what the LLM is capable of, what is its role in the agentic AI system, how the actions are, or how the actual actions are being done. It is only via tools and not by agents. Agents can only generate text. So it can write the research paper for you, but it cannot search the web for you. It will only write a research paper based on the training data the LLM was trained on. So the LLM, let's say it was trained 2 years ago. So between that time and today, so which is 2 years, there would have been a lot of advancements in your research field, which the LLM will not be having access to. So a web search is a very essential thing for you if you have to build an agent for writing research papers. So that's where these web search tools, archive search is all essential. You cannot just leave it to the LLM. So the LLM will only tell you, okay, please do a web search, please do an archive. That is what the LLM will come out with. And it will also give the search terms for archive. It will also give the search terms for the web search. And next you have to use those search terms, and then you have to invoke your tools. So these tools are nothing but, it could be API calls. It could be Python functions. Most of the time these are just Python functions, or it could be some kind of API calls to the web, or it could be API calls to the database. Okay, so the possibility is, that is where I said why the LLMs would give us wrong tool names to be used for completing our actions. So to handle that, you have to, when you call the LLMs, when you invoke the LLMs, you pass instructions. So you have to strictly say, these are the tools, do not hallucinate for any other tools. Loops and overthinking. So we spoke about this reflection pattern. So reflection pattern, there is a generator component, there is a reviewer component. So the generator generates, the reviewer reviews. So the reviewer keeps saying that always it keeps finding with the content, it finds problems with the content being produced by the generator, and it always gives a feedback. Okay, so you've been doing this 10 times. So 10 times you've been calling LLM1 for the generator component, and 10 times you've already called LLM2 as part of the reviewer component. So you've made 20 LLM calls, which is a very costly affair. And it has somehow got into an infinite loop, because the reviewer component is always finding mistakes with the generator component. So in order to break this loop, you have to manually enforce that, okay, beyond 5 number of iterations, I do not want you to keep finding mistakes. Even if you find mistakes after the 5th iteration, you please end my orchestration. You please do not orchestrate back to generator. So that has to be emphasized in case of looping and overthinking. So when you build your agents, you need to ensure that the LLM doesn't end up picking wrong tools, doesn't get into a looping problem, doesn't overthink. It doesn't give, it gives outputs in a certain format. So all these things you have to ensure when you build an agent. Context loss. So what do you mean by context window? So the communication history that has been happening right from the first step that the agent is doing to the last step is maintained as a context, which is retained in your state. So every agent will have a state. So all the entire information that is being flown from one phase to the last phase of the agent is being tracked there. And in the case of, let's say, generator reviewer loop. The first time the generator has created a research paper and the reviewer had given some feedback. So the first feedback from the reviewer is being tracked. The second feedback is also tracked. The third feedback is also tracked. So when you call the generator for the fourth time, you pass in the feedback from not only from the third iteration, but you will also pass in the feedback from all the 3 iterations back to the generator. All right. So that is what is context here. So you have to ensure that your context window doesn't exceed. Whereas if you start tracking the research paper that was outcome by the generator for all the 5 iterations, you can imagine what would happen to your context window. So you need to take that judgment call as to what you have to retain in your context and what is not required. What will cause a problem? What will be helpful? So all those decisions have to be taken here. Finally, invalid outputs. So this is somewhere similar to the unpredictable outputs that we discussed here. So other possible problems is bias. So we have heard about the biases that were created, that were present in the earlier models of Google, released by the models of Google. Like Gemini initially had a problem with it was being a racist. So all those kind of bias related problems have to be verified if you are developing an agent, not for your personal use, but at a larger scale. Then you have to be aware of biases that can come from the agents, because the underlying bias is actually from the LLMs. So when LLMs have bias, the agent is also prone to that bias. Yeah, cost and scaling. So all these patterns that we spoke about. So the reflection pattern is in fact a costly pattern. So you need to be aware of what is the cost, or what is possible or feasible for you to build your agent. So that cost factor also has to be kept in mind. If you go for an overly ambitious reflection pattern wherein the feedback loop between generator and reviewer happens beyond 10 times, 20 times, then you need to understand that accordingly your cost also increases, because that would be if you do this feedback loop 10 times in the reflection pattern, there would be 20 LLM calls. So which is not a easy thing. You have to also be cautious about the cost that will be incurred under the underlying agent pattern. Scaling. So if you are deploying this agent for a larger audience, to be used by a larger audience, then you need to ensure that everybody's context is kept separately. Everybody's state data, the agent state's data is kept separately. Handling sessions is done. So each user would have its own session, and again within a user session, the user can make the agent do multiple things for him. So for example, user 1 can ask the agent to write a research paper on embedding systems, and the same user can also ask the agent to write a research paper on say microprocessors. So these are like again 2 different contexts within the same user session. So all those things have to be taken into consideration when you are building your agent systems. Cost is one aspect. Scaling, what level of what amount of audience you are going to have for your agent, the users, end users of the agent have to be considered, and accordingly you have to build your or ensure that your systems scale up. So prompt. So again, prompt is it is the language of communication between LLM and the agent. So the agent communicates to the LLM via prompt. So in order to have an efficient prompt or an efficient way of interacting with the LLM, making the LLM to do things very effectively for you, reason out very effectively for you, you need to ensure that your prompt has these 6 components. So the first component, the very first line of the prompt, you need to tell the LLM who the LLM is. So for example, you're going to say, you are a research specialist who can identify topics for which solutions have not been built. So that is an example of assigning a role to the LLM. So that role assignment is very important. So even this prompt which I just said, it is not very complete because I just said it is a research analyst, it can pick topic, but I didn't specify the domain. So I should specify the domain in order to make the LLM be more efficient for me. So I could say that, okay, you are a research topic picker for embedding systems. That way the LLM knows, okay, where it has to focus its knowledge on, and it will give you effective results. So the very first component of a prompt, the very first part of the prompt has to be the role of the LLM. And the second part, you have to specify what is its task, what it has to do. So in our example, we are going to say, you are going to pick all the last 2 years research topics from archive, and you are going to find out at what level the solutions are built, how efficient or what kind of benchmarks the solutions have returned for the problem. So in that ways, you can build a newer solution for the same problem and with a higher benchmark. So you can specify all those things, what it is supposed to do, the list of tasks that it is supposed to do in order to pick a topic is what you can specify. So first part is role, second part is task. Third part is constraints, what it is not supposed to do. Like, okay, you cannot go and do a web scraping. You can only do an authorized web search. You do not need to return me any topics other than embedding systems. I want your output to be returned in a certain way. So all possible guardrails within which your LLM has to return its response is specified under the constraint section. And then this is process. So in the process of picking topic, you can make use of tools. So when you specify that, it doesn't mean the LLM is going to use the tool. Rather, it will send back a response saying, okay, tool has to be invoked, and whatever tool you need to invoke, it will tell the tool name. It will also put in values for those parameters. So I said, basically the tools are nothing but Python functions most of the time. Okay, it will return the parameters for the functions. It will return the parameter values for the functions. And using those parameter values, you have to invoke the tool outside the LLM. Okay, so the LLM is not going to invoke the tool for you. So it will only return the tool parameters that have to be used. So this is the process that you have to specify. Say that, okay, in the process of picking topics, you can search the web, you can look into archive, and accordingly it will do things for you, come out with a plan. Fifth one, inputs. So you can provide your research topic, tentative research areas that you are looking for as inputs to the LLM. And finally, you can specify how you want the LLM to respond to. So list of research papers, list of problems, corresponding benchmarks, statistics, and all that can be given as a predefined format to the LLM. So when you invoke the LLM, in the prompt, you can specify this is how I want my output to look like. So these are the main components of a prompt. Prompting strategies. So again, there are several ways of prompting. So these are the anatomy or the different parts of a prompt. This is like, how do you want the prompt to work? For example, this workflow process. How do you want to define the workflow process? You could use one of these strategies to define it. So chain of thought. So let's say you want the agent to solve a Sudoku puzzle for you. Okay, So you can tell the LLM, you can provide inputs to the LLM as to how it can solve the Sudoku puzzle. So first, check each and every row if there are any possibilities or if any of the unfilled boxes can be filled in. Then look for column wise boxes. Then you can look for the smaller grids within the bigger grid. So you can pass in such kind of chain of thoughts to solve puzzles. So how do you like the LLM to proceed? How do you like the LLM to reason out in order to solve something, in order to generate something? So in the case of a research paper, you can say, okay, right away, don't start creating my research paper. You analyze, you figure out, you cross-check against last 2 years of paper. You cross-check against this repository, see if there was any similar research area. So all that step-by-step reasoning you can provide. So that is what we call as chain of thought. Tree of thought is what are the different possible ways to execute a task, and then which possible way returns the maximum result. You ask the LLM to analyze that and find out the most optimal path of solving a problem. So that is tree of thought. Iterative planning is okay. I plan, execute, revise, and then repeat. So this is what we typically use in the we use in the React pattern. So you come out with the plan, you execute the first step, the results of the first step are sent back to the reasoning LLM. Then it will check the output of the first tool, and if it is satisfactory, then it will decide whether the second tool has to be called or whether it can generate the plan or reasoning or whatever it is supposed to do. So you can make, providing the prompt in this iterative fashion, you can make the LLM to work in a loop. Decomposition, we've already seen enough. Reflection, so if you leave the decomposition task to the LLM, then it is like you are providing more autonomy to the agent. Okay, you are letting the agent break down the task and work upon it. So reflection or self-evaluation, so based on the job of the LLM, you can say, okay, your job is only to criticize the answer that you had given me earlier, or criticize the answer that was given by another agent. So that is another prompting strategy. Verification. So let's say you are asking the LLM to solve some mathematical calculation for you. You can use a calculator tool to verify the answer. And so you can ask the LLM, okay, you give me an answer and you have to verify that if that is the right answer using a calculator tool. So the LLM will generate an answer for you. It will then tell that, okay, call this calculator tool with this input. So the LLM will output its own response. It will also output a tool call that you have to initiate this tool call with so and so parameter value. So that thing also you have to specify using prompt. So based on your use case, based on how you design your agent, you can use one of these prompting strategies. Tools. Okay, so far we were only focusing on LLMs, focusing on what are the potential problems with LLMs, how they can be mitigated, and then we saw how prompts have to be specified. Now next is the next building block in the agent is tools. So how do we create tools, and how do we allow the LLMs to access the tool? So this is the tool anatomy. So when you create a tool, which is, let's say it's a Python function, so you provide a tool name, you provide a description for the tool, and then the parameters to that function or the inputs to the tool, you can use a schema, input schema. So rather than you going with the conventional approach of having parameters, this pedantic model is a more restrictive way of defining parameters to the tools. We'll see about this in the later slide. And then this is about the actual tool function that it is supposed to perform, execution logic. the core functionality of the tool is built here. And then this is the output format in which the tool has to provide its response. Okay. So when not to use tools. So if the LLM itself can provide an answer, if it is a simple reasoning, simple calculation, you can leave it to the LLM. When the LLM does not need access to external data, then there is no need of tools. When you want to work on your proprietary data, then you need to use a tool, you need to use a RAG. LLM will not be sufficient here. And then again, when there is a domain mismatch, when you find that, okay, LLM is usually trained on the data which is available on the internet. So if there is something intense financial activities that you have to perform, or intense medical operations, the medical activities, if it has to be carried out, then an LLM may not suffice here. So in that case, we would need to use an exclusive tool. Pydantic models and structured outputs. So Pydantic models here, the outputs to the outputs, the structured outputs that you want from the LLM, in order to avoid any unpredictability, you can use structured outputs. And the tool inputs, if you want to be very sure what should be the inputs to your tools or what should be the outputs from your tools, then if you have to enforce that, Pydantic models in Python is the solution for that. So what these Pydantic models does is it automatically validates your inputs and outputs from the LLM if it is complying to the data types that it is expected. And it enforces the schemas that the LLMs are supposed to follow while generating the output. And if there are any errors to be handled, so all this is handled by Pydantic models. So I think it's time that we look into some code for now. So this is a basic agent. So here if you see, so this is how you build an orchestrator. So basically here the agent is built using LangGraph. So we saw that an agent has 3 building blocks, and the third one was orchestrator. So this is how orchestration is done using LangGraph. We use a graph data structure. LangGraph uses a graph data structure. So graph is basically you have nodes and then you have vertices or you have edges connecting those nodes. So your flow is predefined and you would not get into loops. So if you want to loop things, that is also possible. So if you need to have a controlled workflow in the agent, then the graph data structure is one thing which makes it possible. And LangGraph uses the graph data structure for the orchestrator part of it. So here if you see this agent state, that this is the state of the agent, which basically contains the data that is required for throughout the workflow of the agent. So question is basically the question that is being asked by the user. Attempts is the number of iterations the agent is looping through. Solution is what is the final answer. Reflection is what is the reviewer component, is it okaying the result or it is failing the result from the generator. And these are other messages. So right now these are the various data that is being tracked within the agent, so which is what we put it into a state. So here if you see, this is how we build the agent state. So this is the name of the state variable, and we use type dict data structure to keep track of this data. So now going back to the orchestrator component, if you see, this is the entry point. So there are 3 nodes here. So there is an attempt node, there is a reflect node, and then there is a retry with tool node. So there are basically 3 nodes in this graph, and the entry point, so where the graph starts is from the attempt solution, and from the attempt solution it moves on to the reflect. So edge, this is where we are adding the edge to the graph. So the edge is between attempt solution to the reflect node. So the flow comes from attempt to reflect, and then the second one is a conditional edge. So from the reflect, how does it go? So for that, it can go to more than it can go to this node or that node. So that decision is being taken by this routing logic. So here if you see, so we've set conditional edge. So conditional edge always has a function to decide where the routing has to happen. So here we check if the attempts, we've been keeping track of the attempts in the state variable. So if the attempts is more than 3, then you please end my graph. But if it is, if the reflection state is correct, then also you can end my graph. If the reflection state says, no, you have to call a calculator, you have to call a tool to do things, then you have to invoke the retry with tool node. So first case, whatever be the outcome of the reflection, if I'm exceeding more than 3 attempts, I don't want to get into a looping, forever looping, and end my response. If the response is also correct, end my graph. If not, if the response says, okay, you have to call the calculator, then you have to invoke the retry with tool node. And okay, so this is how we've built the orchestrator component. Now let's get into this node, the details of this node. Attempt solution. So here if we see, we have a prompt. So the prompt, if you see, there is 2 parts to this prompt. One is system message. So system message, basically it consists of the role, the task it has to perform. So all those things are typically specified in the system message. And the human message, whatever questions the person who is interacting with the agent wants the agent to solve, those questions are put into the human message. So so here if you see, the prompt that is given to the attempt is, you are a careful mathematical reasoner. So it is a very basic prompt, and whatever questions the user had asked in, that is being flown into this human message from the state variable. And then there is a reflect. So this is a simple reflection pattern. So here we say to the reviewer, okay, you critique solutions for correctness. And then we say what, yeah, so there is a reflection prompt here. So this reflection prompt is specified here. So you are a critic agent, review the attempted question. So this is the problem. This is the solution from my attempt node. And then the task is identify errors in reasoning or calculation, whether a calculator tool should be used, how to improve the next attempt. So this is the entire prompt of the reflector node. And the reflector node, again, it invokes LLM. So here if you see, the attempt node also invokes an LLM using this prompt. So this prompt has the user query in it. And so this function, whatever the LLM is returning answer, so answer.content, this will actually contain the actual response from the LLM. And the attempts, the number of attempts, we modify the state variable to add 1 to this attempt that has been done so far. And whatever messages the LLM has returned, we put into the state variable, state of messages. So this is how at every step we keep updating the state for what the agent is doing, right? And when we move on to the reflect node, when the flow, orchestrator flow takes the control to the reflect node, it takes the essential data from the state variable. So the state variable has the question, the state variable also has the solution from the previous node, attempt node, and all those, both the question and the solution is being passed to the reflect node. Then we invoke the LLM from the reflect node, and when we invoke, we pass the entire content and whatever messages we get from the critic node, that is also added to the state variable. So if the control comes to retry with tool node, what we do is we look for using this regex pattern. Okay, we search what has to be the parameter that has to be passed to the tool. So what tool has to be invoked and what the parameter of the tool has to be is present in the reflection part of the state. Okay, because that's where we put the output from the LLM here. So here if you see, the response from the LLM is present in critic and the actual content is present in content attribute. We take that and we have put it into the reflection attribute of the state. Okay, so that is being accessed in the tool. We get the parameter, tool parameter, and then once we get the exact tool parameter, we use expressions to run the expression and then find out the answer. So here if you see, the question that has been asked is, what is the derivative of 7 to the power 4? So this is the question which has been asked by the user, and we initialize the state. So when we start with the agent, the attempts are 0, there is no solution given, there's no criticism from the reflection component, and there are no messages. So this is where we call the app.invoke. We can either use app.invoke or we can use a stream function to run the orchestrator. So this entire graph, the orchestrator is being built in this graph, and the graph is compiled and available in app. And the agent is invoked using app.stream or app.invoke, and we pass the initial state when we invoke the agent. So the final output would be available in the solution variable in the state. So this is a very basic agent wherein you just get to see the orchestrator, the LLM, and a basic tool. And this tool here is actually not given as a tool to the LLM, but it is created as a separate node in the graph. So this is a slightly more advanced version, wherein here if you see, we had used Pydantic models to build the input and output to tools, the output from the LLM. So all those have been defined using Pydantic models. So here if you see, there are 3 Pydantic models. So this is the input, tools input. This is the output from the attempt LLM, and this is again the output from the reflect LLM. So in this way we specify, okay, I want my outputs in such and such a way, and it will automatically verify whether the LLM is returning this critic as a string variable, whether it is returning as yes or no. So all those checks will be automatically be done by the Pydantic model. So this is a base Pydantic model. Using that, we define all these classes. Likewise, here if you see, the calculator is built as a tool itself. So we use a base tool LangChain class. We built the calculator tool using this base tool LangChain class, and this here we have only just one tool that is available to the LLM. And so when you call the reflection prompt, you have to specify to the LLM, okay, these are the tools that are available to you. Only you can use only these tools and not any other tools. So this is a placeholder variable, and when you invoke the LLM, you pass values to all the placeholders which are there inside the prompt. So this is one placeholder, this is one placeholder, and the solution from the attempt prompt is another placeholder. So as the graph gets executed, you will get to know the values of solution. When the graph is invoked, you will know the value of problems. So that's how it is. So here if you see, there are only 2 nodes in the graph here, because tool we have kept it as separate node. I mean, we didn't have it as a separate node. we are passing it as a tool to the reflector LLM. So there are only two nodes. The entry point is attempt, and then this is conditional edge, as we've seen earlier, and the rest are all the same. So this just uses a more elaborate prompt as well. So here if you see, it says, okay, what is your role? What is your task? What are the tools available to you? Then this is the problem. Even this prompt is not elaborate, but to some extent it meets this simple task of performing mathematical calculations. So for that, this prompt is sufficient. Any questions so far? Or should I take questions at the last? Okay, I think I'm kind of done. So how do we evaluate agents? So we have built the agents. Now, how do we evaluate? So usually when we build any software applications or software systems, we always do unit testing. We do system testing. When as part of unit testing, we figure out what has gone wrong with the code, for what use cases, test cases, the code is not working correctly. We make changes to the code accordingly. Here in the case of agents, how are you going to test the agents that you're building? So you have to test them on for various parameters. So correctness. So in the previous example, I mean in the code that we saw, we need to ensure that, okay, whatever calculations the agent is doing, is it giving us the right numbers? So did it solve the task correctly? So first thing is correctness. So you have a task where it is supposed to process some date fields which are present in your input. It is not processing the dates correctly. So the research papers, you have LaTeX formulas and it is not processing it correctly. So do you need to build a separate tool and give it to the agent? So then you need to check the efficiency of that tool. You need to provide some 20-30 LaTeX formulas and see if your agent is now identifying the formulas correctly, whether it is interpreting it correctly. So you have to check for correctness first. So for fixing the correctness issue, you can either build additional tools, and then you have to identify where the agent is failing. That is the first step. And after identifying that failure, you need to fix that failure which is occurring. You can either build additional tools, you can either refine your prompts so that the LLM knows how to process it correctly. So in the case of typical software applications, it's always fixing the code. But here it could be different things. You either need to build additional tools, you need to either refine your prompts. Most of the times it's about refining your prompts. So you need, as you refine prompts, you will get to know how we maintain versions for the code. We have a repository to ensure that the version control is taken care. Likewise, your prompts that you build as inputs to the LLMs, that also has to be versioned, because every time you keep changing your prompts, and sometimes you figure out, okay, my yesterday's prompt was working better than today's prompt. So prompt versioning is also important here. You cannot consider your prompts as okay, it's just a constant, it's just a string, and you cannot ignore it. Prompts are more important than the code here. Reasoning quality. So is my LLM reasoning correctly? Is it failing somewhere? It could fail because, okay, last 2 years of data, it doesn't have in its training data, it doesn't have access to that. It was trained 2 years ago. So, okay, so why it is not reasoning? Why it is not giving me the correct thing? It could be because there is a RAG missing, or it is because there is an archive repository you have not allowed the LLM to access to. So all those things have to be sorted out. So this is one example. So there could be similar such other example where the LLMs do not have the full capability to, you have not provided the LLM the full capability to perform its task. So you need to check if the steps are valid. Tool use quality. So here you need to ensure the LLMs are not hallucinating. It is using the right tool for the right task, and it is also putting in the correct parameter values in order for the agent to make that tool call. Control flow. You need to ensure that the flow within the graph is happening correctly. The data flow is happening correctly. The looping is happening correctly. It is not getting into infinite loops. All those checks, the control flow also has to be evaluated or verified for. Robustness. So when there are any errors, when the LLM is not, when we are not able to connect to the LLM via APIs, when we are not able to connect to the tools available on the internet via API calls, are we handling those errors efficiently? Because when your agent fails, you cannot remain clueless as to why the agent failed. You need proper error messages why the agent had failed. So you need to ensure that all the errors and missing information are appropriately handled. So this debugging stuff is something which you cannot ignore completely. You have to ensure that all the errors and everything are handled well, so that debugging the agent later is much more easy. Performance. So this, I think we've already touched upon it earlier. This is about the number of LLM calls, the number of tokens that you pass to, because all those they come under cost, and how efficient your systems are. How quickly it can give you responses. So the more number of iterations that you do between generator and reviewer, you need to understand that your agent is going to take a whole lot of time. So the performance, is it acceptable? So again, performance is another aspect on which you need to evaluate agents. And that's all. That's the end of the session. Any questions? I assume there are no questions on this, and hope the session was useful.
Participants, if you have any queries, you can post in the chat box. Thank you, ma'am. Thank you. Participate once again. Feedback link is posted in the Zoom chat box. Please fill the feedback form. As well as we posted the quiz also online quiz. You have to attend that. Not yet posted any questions, I think, Noma.
Is there any free AI agent? Yeah, right now you can have hands-on on anti-gravity. Though it is basically an IDE for code, it can still do other things. It can create documents for you. It can create question answers on any domains that you'd like to be quizzed upon. It is free to some extent. It gives free LLM calls to some of its most premium models. That is, and ChatGPT also for monthly 400 or something you have. You can use it. You can use the LLM call. You can get the API key, and you can build your own agents. So that is also possible. Any other questions? right now anti-gravity is free, and I think everybody should make use of it and then try out what it has to offer, and then later when it put a cost towards it, you will be able to take a call as to whether it's useful, whether you can shell out that money and continue to use anti-gravity or not.
Participants, if you have any queries, you can type in the question answer session. Feedback link is posted in the Zoom chat box. Kindly fill the feedback form. I think no further more questions, ma'am. Shall we wind up the session, ma'am?
Yes, ma'am.
Okay, ma'am. Thank you, ma'am. Thank you for delivering such an enlightening session
I'm
on
glad
intelligent agentic system. Your depth of knowledge, clear explanation, and impact.
Thank you, ma'am.
It's my privilege to present the formal vote of thanks on behalf of the Department of Computer Science and Engineering and Department of Cyber Security of Dr. MGR Educational and Research Institute. I wish to thank our beloved Chancellor, Dr. A.C. Shanmugam sir, our President, Engineer A.C.S. Arunkumar sir, for his constant support in all our journey. Our sincere thanks to our Vice Chancellor, Dr. S. Geeta Lakshmi ma'am, Rector, Dr. D. Vishwanathan sir, Registrar, Dr. C.B. Palanivelu sir, Senior Additional Registrar, Dr. P. Kalidas sir, and Additional Registrar, Dr. V. Cyril Raj sir, Advisory Committee Member, Computer Advising sir, Computer Sciences, Dr. K.M. Mehta sir, Joint Registrar, EPA, Dr. L. Ramesh sir, Dr. N. Yetiraj sir, Dean Engineering and Technology. A special thanks to our Dean and Head of the Department of Computer Science and Engineering, Dr. S. Geeta ma'am, and HOD of Department of Cyber Security, Dr. P. Dinesh Kumar sir, for their incredible support and guidance of the event. I extend my heartfelt thanks to all the faculty members of Department of Computer Science and Engineering and Department of Cyber Security. Next, I wish to thank all the additional HODs and deputy HODs of CSC and Cyber Security. A heartfelt thank you all to all the eminent speakers for your valuable contribution for this 5 days online faculty development program. Your insights and expertise have truly enriched the experience for all of us. My sincere thanks to Mr. Saravanan Elumalai sir, Deputy Dean, University official website, who helped us throughout the program. I would like to thank our system admin, Mr. Paramasivam sir, and for their making this event successful in online platform. My sincere thanks to my co-organizer, Mrs. R. Selvamina ma'am, and all the faculty members for in CSC as well as CF, that is Cyber Security Department. Finally, I extend my heartfelt thanks to all the participants. Your presence has made this event truly interactive and enriching experience. We look forward you to join in the upcoming events in the future. Thank you so much. Have a nice day. Thank you.